Hi! Okay, kids, welcome back to your little mini lecture here on reviewing physical versus chemical changes. A lot of this stuff is stuff we already know because we learned it all the way back in Unit 1. We're just kind of revisiting it here now that we're in Unit 5. Hopefully you looked at the title of Unit 5. Unit 5 is called Chemical Reactions, which means, what are we primarily looking at in this unit? Chemical reactions. So this does mean we're going to have to review our knowledge about chemical reactions. So previously, in Unit 1, we kind of defined a chemical reaction as the Beauty and the Beast song. There must be something there that wasn't there before, right? It turns out it's just a little bit more complicated than that. It's a base definition, it's good, it's a working definition. But in order to make a chemical reaction happen, you have to have particles, chemicals, that collide with each other. When those particles hit each other, if they do so with enough energy and with the right positioning, their chemical bonds may break. So recall, your chemical bonds are what hold your atoms within your particles together. If they're covalently bound, it means they're non-metal atoms held together. If it's ionically bound, it's a metal and a non-metal, or a cation and an anion, right? So in order to make a chemical reaction happen, we have to have these particles hit each other and their chemical bonds have to break. Then what happens is the atoms within those particles will rearrange themselves. You kind of make this like alphabet soup. This then causes new chemical bonds to form. So these new bonds will result in the formation of new particles. These new particles will have new and different properties from the original matter. So this is a chemical reaction. So let me give you like a particulate model of what this would look like. Let's say I had this chemical here, chemical pink, blue. Excuse me. These atoms are bonded together. They are held together by some force of attraction, whether it be covalent or ionic, doesn't matter for the purposes of this model. If this thing comes into contact with another atom, let's call it red, what's going to happen is these things are going to hit each other. If they do so with the correct amount of energy and the correct orientation, we can make chemical soup, essentially. So let's say these particles collide and they do so like right here. What's going to happen is this rearrangement. It's like like in those old rom-coms, like the classic trope of like two people that are walking in the hallways with like their hands full of papers and books and bags, whatever, and then they bump into each other and their stuff goes flying everywhere and they're scrambling to pick it up, and then they like look up at each other and they look into each other's eyes and they're like, oh my God, you're so beautiful. I want to love you forever. That's essentially what's going on here. So these particles will come into contact, they'll collide, they're going to rearrange all their stuff, and then they're going to form this beautiful relationship in which they're going to carry each other's particles, create something totally new than what they were before. So these things are going to hit, they're going to rearrange, and eventually, we're going to get some new particles with new and different properties than what we ended up with before. But the important thing to remember is that all of the original atoms are still represented somewhere. So this could be an example of what a chemical reaction looks like on this like particulate level. In a physical change, we know there are no chemical bonds that are broken or formed, because that would mean changing identity. Physical is all about keeping identity. So, therefore, the identity of the original matter does not change. Everything that was present before is present in the exact same way after in terms of its actual chemical makeup, its identity. It just has different properties. One specific example of a physical reaction that we looked at is a phase change. So phase changes are physical changes. Physical changes. So chemical bonds are not broken or formed. Instead, what we are breaking or what we are disrupting is intermolecular forces. So these forces of attraction that hold our particles together need to still be broken in order to get these things to change phase. This causes them to break apart from each other and come together. So let's say we had something like water in the solid phase. Here's all my little water particles. They have a little bit of motion. They're wiggling around through each other. If I added some energy to the system, that would cause my particles to vibrate even faster. They're going to shake their booties. And what's going to happen is eventually some of those IMFs are going to break as those particles are moving even faster. And it's going to cause them to turn into a liquid form. So they're now going to be able to kind of flow over each other a little bit more. They've got a little more motion than they did before. And they're a little bit farther spread apart. If I add even more energy, these are going to totally break nearly all their IMFs as they're going to transition to the gaseous phase. But the identity is still the identity. My white circle is still my white circle. Okay, so we learned about some evidence for physical and chemical changes previously in Unit 1. What I want you to do is pause the video here, see how many you can come up with your table groups on your own, and then you can check in with my answer key that I'll post on Canvas or in the resources to make sure you hit all the right ones. So pause the video here, brainstorm with your group, write down as many as you can, check your answer key, then come back. Okay, I'm trusting that all of you were obviously sweet little baby angels and you did exactly what I said. Obviously, it works every time. So now let's talk about how can we model chemical reactions? What do these things actually look like? So we can represent chemical changes through a chemical reaction equation. There's a couple of vocabulary words we're going to need to learn as we do this. So we're going to keep building our chemical vocabulary. Let's say you had the original matter at the beginning. That original matter goes by the name reactants. Oops, and I totally spelled this wrong. Reactants. There we go. So this is your original matter, all of the stuff that you had present before. So the reactants in my model equation up here would be pink, blue, and red. Those are my two reactants. So when these things come together, when they react, they're going to produce my products. My products are my new matter. This is the new stuff with new chemical bonds, new properties that I've created. Do you remember what this arrow means all the way back from when I first showed you a chemical reaction equation in Unit 1? It's yields. Yields or produces. So the way you would read a chemical reaction equation is you would say your reactants yield your products, or your reactants produce your products. So reactants, left side of your arrow, original matter, they react together, products, new matter, right side of the equation. So here's what I want you to do with these. Take a look at these three reaction equations. Before we can jump into chemicals, we're going to use shapes, keep things easy. So this thing right here, those would be my reactants. This thing here and this thing here would be my products. What I want you to do is pause the video and stop and talk with your table group. What patterns do you see? Oh, LOL. What patterns do you see within these three reaction equations? What's the same about them? What's different about them? What do you kind of notice? You can write your observations off to the side over here. So pause the video, talk these things out, and then come back to hear more. Okay, obviously my sweet baby angels did exactly what I told them to. Oh my God, you're so good today. Wow. So here's some things that you should have noticed. Everything that's present on the left is also present on the right, but it's rearranged. It looks different in a different form on the left than it does on the right. This is really what the chemical reaction, like that's the definition of a chemical reaction, right? I took original stuff, I broke it apart, I put it back together in a different way. The other thing you should notice is the same number of things are present on the left and the right. This goes back to the idea that we talked about all the way back in Unit 1. So in a chemical reaction, the reactants must have the same number of particles as the products. And when I say number of particles, actually I'm going to change this word. I'm going to make it number of atoms. Particles is too vague. We gotta make it a little bit more specific. So it's got to have the same number of atoms. So therefore, the two sides of your reaction equation must be equal. For instance, if I started with 1 telescope on the left, I have to have 1 telescope on the right. I'm talking about this one right here. 1 satellite on the left, 1 satellite on the right, 1 astronaut on the left, 1 astronaut on the right. So the same number of things is present before and after. But if I take a look at my particles, my general word, this is why I couldn't use this before, is this has 1, 2, 3 reactants, but only 1 product. That number does not have to be equal. That number doesn't matter. It's about just the number of things, the number of atoms that make each of those things up. So this idea of having the same amount of stuff before that you had after, this is one of our most important fundamental concepts we learned. This is the law of conservation. So law of conservation of mass and matter. So think back for me to the phenomenon video that we had talked about, or the phenomenon that we had watched. Does this obey law of conservation? What was the mass before? What was the mass of the system after? Think, what could have potentially happened then that caused this mass difference here? Think about, what did the mass increase, decrease? What could have happened to it? So the way that we can model these chemical reaction equations, we can do it in 2 ways. We can use a particulate diagram. This is something we've been getting a little bit familiar with in our gases unit, modeling these things as particles. We're going to do a lot more practice with these. And the other way we can model them is using what's called a balanced chemical equation. And this is what you are going to learn about and what you are going to practice next. Bye!